In this video we look at standard deviation. So standard deviation is a measure of spread, so how spread out the data is. Before we get to the actual description of standard deviation, we should talk about what a deviation is. So a deviation is really just the distance between an individual data point and the mean itself. So an individual value in the set and the mean. So we calculate the distance between those two. So there are two ways to look at deviation, one for a population and one for a sample, and that's because we talked earlier about how a sample mean and a population are a little bit different. Not a lot, but a little bit, and that causes us to have a deviation that's a little bit different. So the deviation is quite simply just equal to the x value, so any given data value, minus the mean. If we just want to find out the distance between the two, we subtract them and we get a deviation of x minus mu. So just a reminder, this is equal to the population mean. And then for our sample, the deviation is just equal to x minus the sample mean, and we used x bar to represent the sample mean. So that's what a deviation, or how we find a deviation. When we're talking about the standard deviation, we're trying to figure out essentially on average how far is each data point from the mean. So that's a quick description of what we're doing here. We're trying to find out on average how far is each piece of data from the mean. I want to show you a couple of different formulas to do this. They look kind of confusing, but we'll work through an example so you can see exactly how this works. So for a population, the standard deviation, we use this symbol, the lowercase letter sigma, for standard deviation. So that's a Greek letter sigma, and it's a lowercase. And we say that the standard deviation, so maybe we'll just label this so you know what it is. That's the standard deviation, is equal to the square root of the sum. So again, that's just a capital letter sigma. That means the sum of the deviation. So remember, we just talked about the deviation as just being the distance that each data point is from the mean. We square it, and the reason for squaring it is that we want to make sure that all of the deviations are positive. We want a way to represent the deviations so they're positive. If we don't, then what happens is we'll get some that are positive, some that are negative, and some of them will actually end up sort of canceling each other out or eliminating each other. So we square them all so they're all positive. We divide by the number of data points because we're trying to find an average, and then we take the square root here, to undo the effect of squaring. So this gives us the standard deviation. So it's an average of how far each data point is from the mean. We'll look at how to calculate it in an example. For a sample, instead of the Greek symbol sigma, we use S for standard deviation, and you might have guessed this mostly. For a sample, the standard deviation is the sum of the deviations, so x minus the mean, sample mean in this case, so x bar. And in this case, I forgot a squared here. We need to square that as well. And in this case, instead of dividing by n, we divide by n minus 1. So for a sample, we're dividing by 1 less than the data point. So that's the formula for calculating standard deviation. Again, it looks kind of confusing. We'll work through an example and you can see what that looks like. Now, another measure that's closely related to the standard deviation is something we call the variance. The variance really is the standard deviation squared. So it's that answer we get from the standard deviation before we take the square root. So if you just wanted to compare two data sets and to see which one had a larger standard deviation, you could actually stop before you get to the square rooting part and just look at the variance and see, if you're comparing two sets, see which one has a bigger variance, and that one is going to be more spread out. So here's the formula. No surprise here. It looks just like the one above without the square root sign, since that's what it is. So it's the sum of the variances squared divided by the number of data items. Again, it's not so useful to describe the data because the units kind of are squared and you get these sort of weird things. But in terms of which set of data is more spread out, it's kind of enough to be able to figure that out. So here, same thing, we're going to get the sum of the variances, or the x values minus the means. So x minus x bar, we square those, and then we divide by the number of data points. So those are the formulas for standard deviation and variance. Now let's put them to work here and see what we can come up with. So here's an example. We have a table here, and this table shows the commute time to work. So this is an individual's commute time to work. So obviously, a commute time is not always the same. So this is an example where somebody tracked their commute time, and what we are going to do is to calculate the standard deviation. So the commute times are our x values. The deviation up here is just going to be x minus the mean. Now this is well, we don't know if this is a sample or not, but let's maybe assume that this is the entirety of the person's commute. Maybe they just moved to a new area and they just started tracking. So we're going to assume that this is a population. We don't know that for sure, but that's an assumption I think that we'll make here. So we need to find x minus the mean. So we need the mean. In order to find the mean is just the sum of all of the x values divided by the number of x values, and if we take all of these values here, add them all up and divide by how many there were, we should get an answer of 72.8. So that's the population mean. So that's the mean of all of the commute times that we've seen. So in order to calculate the deviations, we need to take every data point, in this case 55, and then we subtract the mean. And if we do that, we'll get, let's see, negative 17. I'll just put it down here so I have enough room. Negative 17.8. And we repeat this process all the way down the table. So this is a long process, but it's not a hard or a complicated process. We just keep going. I'll write out the first couple, and then I'll just write in the answers here. So we take the data point, in this case 68, subtract the mean, and that's the deviation. So we'll put that in this cell, or this box here. So we get 23.04. And again, we continue that all the way down. Hopefully I can transpose without making any mistakes here. So we get negative 13.8. Again, we're just taking each of these data points and subtracting the mean. Many of you are probably thinking already that a spreadsheet would be very useful here, and that's true. You do need to know how to calculate the standard deviation by hand and using technology. So, almost done. So there are all of the deviations. Now if we flip back to the screen here with the formula, we needed not just the deviations, but we needed to square the deviations, and we need the sum of those. So we need the sum of the deviations squared. Let's see if we can do that now. So this column right here will be the deviations squared. So x minus the mean squared. Now if you get good at this on your calculator, you can kind of do both the deviation and the deviation squared at the same time. It saves you typing in the same numbers again on your calculator. So if we take this, all what we're doing is we're taking this value right here in our table, deviation, and we're squaring it. So negative 17.8 squared. All of our answers should be positive because we're squaring all of them. So 17.8 squared gives us 316.84. I'm just going to round to 2 decimal places. And the next one, I just realized I made a mistake in here. 68 minus 72.8 is not 23. In fact, it's negative 4.8. Sorry about that. So we square that, and that's where the 23.04 comes in. 10.2 squared is 104.04. We'll keep squaring these, and we'll fill in our table here. Again, hopefully I don't transpose any of these incorrectly. So 4.84 here, negative 10.8 gives us 116.64. 5.2 squared is 27.04. And 24.2 squared is 585.64. 10.2, we had that one earlier, that's 104.04. Alright, so now that we've calculated the deviations squared, you'll remember that the formula for the standard deviation, I'll just write it over here so we can keep an eye on what's happening here. The formula for the standard deviation, let's try that again. Is equal to the square root of the sum of the deviation squared divided by the number of elements. So we've calculated already the deviation squared. We just need the sum of the deviation. So really what we need to do is to sum this column here. So just add all of these up. And if we add that column up, I believe we get 1,495.6. So when we go to answer or plug these values into our equation here, we get that the standard deviation is 1,495.6 divided by 10, because there were 10 values in our table here. So we plug that into the calculator. So 1,495.6 divided by 10 gives us 149.56, and then we take the square root of that and we get approximately 12.23. So what that means is that on average these data points are 12.23 units away from the mean. So assuming this commute time is in minutes, on average each data point is 12.23 away from the mean. When you're looking at standard deviation, the larger the standard deviation, the more spread out the data is, because every data point is on average further away from the mean. The smaller the number, the more clustered they are to the center. We should also look at the variance here, just so you know how to calculate it. I think you probably know already. Just a reminder that the formula for variance is just the sum of the deviations. Sorry, that's mu squared divided by the number of entries. So in this case, we've already calculated the sum of the variances, the deviations squared. We got 1,495.6. That's a 5. Not a decimal. And then we're dividing by 10. So we get a variance of 149.56. Just a reminder, this is the variance. And this is the standard deviation. So that's how we can calculate the standard deviation by hand. As I said earlier, it is a sort of long process, but it's not a complicated process. Obviously, with a large data set, you're not going to do this by hand. It's important that you know how to do it by hand so that you understand the principle involved, rather than just saying, my calculator is giving me this answer. So make sure that you know how to do it by hand, and we'll also look at how to do it with a spreadsheet. You may have figured out how you can do this table in a spreadsheet, but there are some functions built right into spreadsheets that'll do that for us as well.